Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so we will continue studying regular local rings, and I will provide the gaps last time we have had. So, for example, and also some examples. So, to get more intuitive ideas from geometry especially. So, what we want, so we have started with, so let us recall a definition of regular local ring. So, A M Noetherian local ring and of dimension equal to D. So, we have seen in earlier lecture that this D is less equal to the minimal number of generators for M, which is also dimension of the vector space M by M square over the residue field A by M. So, if equality holds here, then we call the ring to be regular. So, A is called regular if regular local if equality holds. Okay, so so the local rings are usually studied with the help of the associated graded ring. You have seen this also in the proof of dimension theorem, etc. Also, when we talked about Hilbert sample polynomial, etc. and so on. So, for A, we have this object GRMA, which is the associated graded ring of, this is the direct sum of this successive powers quotients. This is called the associated graded ring of A. And last time we have seen that regularity of the local ring is equivalent to the associated graded ring in the polynomial algebra. This is what we have seen, and obviously in the number of variables as D. Okay, and in that proof I have used that the local ring A and this associated graded ring have the same dimension. This I have not proved, we will prove it today. Most of the things we have proved, we have to tie up the things in a neater way. So, that is what we have used, but before I do that, also I have made a statement that if A is regular, then it is normal. And how did we prove? If A is regular, then this graded ring is a polynomial ring, and polynomial ring is integrally closed, normal, and from there I said original ring is normal. So, we have used these two theorems, two things, namely if A is regular local, then the that is equivalent to saying the associated graded ring is a polynomial algebra over the residue field. This we have used, this we have proved by using dimension of A equal to dimension of associated graded ring. So, this we have to prove today, this theorem 1. And another thing I have used is if A regular local, then A is normal. and for this I said use this one, because if this is normal, graded ring is normal, then the original ring is normal. This is what we have to prove. Okay, but before I do that, I want to make some comments about the definition of regular thing. First of all, see, you should view this associated graded ring. So, from A we have gone to associated graded ring. One advantage is this is a finite type algebra over a field, and for finite type algebra over a field we have very strong statement, normalization lemma and so on. That was not in the case of local ring. Another thing is, if you look at the spec, the prime ideals with the Zariski topology and this one. So, this one is now a better one because this is a cone. See, this graded ring is isomorphic to polynomial ring in general. I am talking in general, kx1 x2 xn modulo some ideal j, and this has a property that this is made up of the lines passing through the origin. So, therefore, we have approximated this spectrum by a nice object which has this homogeneous property, and that, namely the cone, that is called cone, affine cone. So, that is spec of this. In an example, it will become more and more clear about the geometry. Okay, that is one comment. And another thing is, we wanted to define in general when the ring is not regular, ring is not local, then we want to define it is called a regular if all localizations are regular. But to do this, we have to prove first that if you have a regular local ring, if you have a local ring, and if all localizations are regular, then the original ring also should be regular. And this is not so easy to prove. For this we need a help from homological algebra. So, after this I will develop homological algebra. So, this statement that A is local, then A is regular if and only if A localized at P is regular for all P. This is not so easy to prove. Because of this, to prove this statement, homological algebra use the use of homological methods in commutative algebra became more and more popular. Okay, so now first I will indicate the some examples first. Of course, some examples we have to decide. So, for example, also we have defined for a singular locus, if I have a affine variety V, so V of the ideal, this is a subset of the spectrum of the polynomial ring, let us say, and we wanted to define what are the singular points. So, the singular points to test whether some point is singular or not, that is what the criterion I stated last time, that is Jacobian criterion, that anyway we will prove it soon. But more important is for arbitrary ring for the spec of A, we want to define what are the singular points. So, sing of spec of A, these are all those prime ideals where the ring is not regular. AP is not regular. So, those are called singular points, and the complement is called non-singular points. So, we want to check that this singular points is a closed subset, and not only closed subset, it is thin, that means it has not too many elements. So, the following two examples will give more light on that. For example, if you try to draw a graph of some curves, let us say cubic curves. So, these are the examples that gives us some idea. So, these cubic curves in the plane, of course, in the plane. For example, if you take the equation y cube minus x square, so the picture will look like this. So, at this point will be the singular point. That is how we will test in Jacobian criterion also, and this is what you have learned from your calculus courses also. This is called a cusp. This point is cusp. Or if you take another equation, that will be y square minus x square times x plus 1. So, this will look like this. This is called a node. This is also singular point. And you see, why is it a singular point? This or this? Here tangent is, here there are visibly two tangents at this point, right. So, the tangent is not well defined. Here also there are two tangents, but there is a double tangent. One is, so they are hidden. No, so they are in the picture it is not seen, but actually they are double tangents. If you write down the equation of the tangent by using your calculus courses, then you will have two tangents here, namely this x axis. Here it will be y equal to x and y equal to minus x, and then another example is like this. So, here this equation is y square minus x times x square plus 1, and I am taking the real picture. So, that I am taking the field is real numbers. So, in this case it is smooth, the point is smooth. So, there is no singular point, no singular point. So, this is what we learned from calculus, but as you see, when you go in higher and higher dimension and more equations, then it becomes more and more difficult to check by using calculus methods. So, we have to have more powerful algebra, and that is provided by commutative algebra. Okay, now before also I go on. So, in the same examples also, now let us do it little bit more abstractly. So, I will prove now that, so we have a Noetherian ring A, may not be local, and we have the spectrum here, and we have learned that this topological space has finitely many irreducible components, and the irreducible components are provided by the minimal prime ideals. So, irreducible components, they correspond to minimal primes. So, the first observation is if some prime ideal P, suppose it belongs to more than one irreducible component. So, think of P as a prime ideal. So, think of that as a point in a topological space, and suppose this point belongs to two irreducible components. That can happen, no. So, for example, if you have somebody like this is irreducible component is. So, for example, if you have equation, for example, if A equal to k xy mod xy, ideal generated by xy. In this case, the picture looks like this. So, this is one irreducible component, this is another irreducible component, and this origin is belong to both of them. So, in that situation, I want to say that point cannot be non-singular. That point has to be singular. That means the local ring at that point has to be non-regular. So, if P belongs to, that is the statement, more than one irreducible component, then P is singular. Singular means, so that is P belongs to that is P, A localized at P is not regular. So, let us prove. So, P belongs to more than one irreducible component means P will contain, so everything, the whole idea is all the geometric statement we will convert to algebra and prove there and go back. So, suppose P contains two minimal primes. See, P belongs to the, P is on the irreducible component, this statement when you translate to algebra it will become P contains that minimal prime. So, P contains therefore two minimal prime ideals Q and Q prime, where these are two minimal primes. And what do you want to show? You want to show this ring A localized at P is not regular, right. So, that means you have to go to localization at P, and because these minimal primes are contained in P, they will survive here and they will continue to be minimal primes, right. But then we have just now seen this ring cannot be regular, that is what we want to conclude. If it is regular, it will be domain, and domain means exactly one minimal prime ideal, namely the 0 1, but we have two minimal primes surviving there. So, therefore, A localized at P cannot be regular. So, minimal primes contained in P, therefore, Q A localized at P and Q prime A localized at P both are minimal primes in this local ring, but that cannot happen because this is a domain. If a regular, if it is regular, if AP is regular, then AP is a domain, and therefore, there cannot be two minimal primes. So, contradiction, therefore, we have proved that AP is regular and that means P is singular. So, therefore, when one wants to draw a picture of a spectrum of a ring where P is a point there, then if at P it is non-singular, that means that P should belong to only one irreducible component. Okay. And in this example, so in this example, for example, it is not seen, there are two components. See, the thing is, we have to do locally, and localization for some obvious reason it is not good enough to see the picture locally. So, localization is not good enough localization. So, for that I will we will study the concept of completion, but I will not come to this now. This completion is like a more magnifying glass, so which will see locally in a neighborhood even better, and also it gives you a better connection with the analysis. So, that corresponds to the power series. So, here we are dealing with polynomials, etc. So, completion will deal with the power series. So, that will give you a more better picture. So, this picture, when you would have looked under completion, you will see that two components are going through that origin. This is what we will check when I introduce a completion to you. Okay, fine. Now, let us get back to our proof of. So, the theorem we want to prove is actually this is what the dimension theorem should be. If A is Noetherian, local, then the dimension of A equal to dimension of graded ring of associated graded ring of A. Okay, so proof. I only have to tie up several steps So, I will be little bit sketchy, but all the proofs you have known earlier in when we did Hilbert functions and Hilbert polynomials and so on. So, now we this GRMA, this is finite type algebra over the residue field. So, this is K small x1 to xn, where K is the residue field of A and the maximal ideal is generated by x1 to xn. So, M is minimally generated by x1 to xn. Strictly speaking, it is bar here, right. So, this is standard, what we call it, standard graded K algebra. So, this is K direct sum m by m square, direct sum m square by m cube and so on. This is the associated graded ring, and this part generates as a K algebra. Graded ring is generated by this first homogeneous component over K as an algebra. So, that is what we know. So, now I am going to imitate what we did it for the local ring, the Hilbert sample polynomial. I am going to imitate that to this graded K algebra, this finite type K algebra, but the definitions are defined by using this x1 to xn, and we have to check that it does not depend on the generating set. That is the major step, but that is also okay. So, let us define what we are defined. So, more generally, so what I am going to do is, I have a polynomial algebra K x1 to xn, and I have an ideal in that. A is an ideal in that, and I have the residue class algebra K x1 to xn mod A. This is K small x1 to xn, and let me call this as A, capital A. This is nothing to do with the original local ring. So, this is A, and I am going to define, I have defined actually earlier lecture. So, I just want to recall, for any m in n, we have defined this A less equal to m, that is by definition. Look at all those polynomials in the small x such that f degree of f is smaller or equal to n. Any element in A is coming from a polynomial, and you put instead of capital X small x. So, this is not unique, the expressions are not unique, but who cares, that you just take them and look at all those degree m polynomials and take their images in this ring and collect all of them and call that as AM. And it is obvious now, this is a K vector space and finite dimensional. So, it makes sense to define this function, that is function from n to n, any m going to K vector space dimension of this. This function I denote by h suffix a, right, because it depends on this. This is called Hilbert function of that ideal. Of the ideal A. And similarly, the Hilbert series, that is capital H A T, this is by definition the series, the coefficients are these values at m. This is Hilbert series. Of A. Okay, now let me give one example, so that you get that this Hilbert function and Hilbert series, they depend on the generating set. This is what I want to show you by examples first. So, suppose you have two variables k x1 x2 and you take the principal ideal generated by x1 minus x2 square. This is my ideal. Okay, then let us write down the Hilbert function of the ideal A at value at m. So, I say that this is 2m plus 1, because what do we want to compute? We want to, this should be the dimension of the vector space A less equal to m over k. This is what I want to check. So, what is this vector space? This is, you just go mod that and take all polynomials of degree smaller or equal to m and then compute the dimension. But I will list all those polynomials. See, for example, 1, x1, etc., etc., x1 power m, then x2, x1, x2, x1 power m minus 1, x2. This is in fact the basis of this, because what do you need? You need polynomial smaller or equal to m, right. So, and whenever there is x2 square, I will replace it by x1. So, I do not need x2 square. So, that is why, and up to x. So, this is a basis for this, and how many of them are there? These are m, these are m, and these are m, 2m, and this is 1. So, this is 2m plus 1, right. So, this is the Hilbert function, and therefore, what is the Hilbert series? This is then 1 plus t divided by 1 minus t whole square. That is easy computation. I will leave it for you to check. You just need only this in the calculation. Okay, so on the other hand, now suppose I have taken this. Now suppose I take, yes. See here, from x1 to x1 power m, they are m in number. From x2 to x1 power m minus 1. Okay, but you see now, this we were talking, what was A? A was k x1 x2 mod ideal generated by x1 minus x2 square. This was our, the small x1 x2 is here, they are modulo this ideal. But I could have also taken, this is also isomorphic to, just forget x2. So, this is isomorphic to kx as a algebra. So, I could have taken x as my generating set, and in that case, what is the Hilbert function then? In that case, it is easier. In that case, if I take this as a representation, see, when I say representation means you want to write a given algebra as a quotient of a polynomial algebra, and there may be many ways to do it. So, for example, this was one way, this is another way, just you forget x2 and then you get kx1. No, forget x1, you get, this is isomorphic to polynomial ring in kx, right. So, now if I use x as a generating set for the K algebra, then the Hilbert function will be not, I do not write a suffix here now. So, in that case Hm will be equal to m plus 1 and the Hilbert series will be whatever. So, therefore, Hilbert function do depend on a generating set of a finite type K algebra. Now, therefore, the only hope is we prove that this degree of that, we prove that it is a polynomial function and the degree of that polynomial function does not depend on a generating set. This is what we will prove. Okay, so, okay, so we are, see, in other words, see this A less equal to m, this gives a filtration of the algebra A, and we have used that to define the Hilbert function. Okay, now for principal ideal you can compute the Hilbert function. So, I will not compute that, but let us, I will just at least state, suppose I have a one polynomial in over a field in several variables, and I want to take the principal ideal generated by f, that is A is the principal ideal generated by f, and then we are taking the quotient algebra. A is k x1 to xn modulo ideal generated by f, and then what is small h suffix f and capital H suffix f, the series. So, I will write the series now. So, because from each you can read the other one, because these are the coefficients, and these, once you know the coefficients you know the series. So, for the 0, if f were 0 polynomial, then it is easy, it is 1 upon 1 minus t power n plus 1, and if f is non-zero, it is 1 minus t power degree of f divided by 1 minus t power n plus 1, and this one proves by induction on n, by induction on n. For f equal to 0, it is really easy, because in that case what is our A is a polynomial algebra. So, if f equal to 0, let us see, it is easy. In this case A less equal to m is nothing but k polynomial ring in n variables less equal to m. This is a vector space of polynomials in n variables of degree up to m, but this is same as direct sum k x1 to xn minus 1 less equal to I and xn power j. This direct sum is running over I plus j equal to m, and I and j are natural numbers. We are interested in computing the dimension of this, but we can easily compute the dimension of this by induction and just tie it up. So, that I will not carry out that calculation. Similarly, same thing you can do it for non-zero f, and for non-zero f the usual trick we have to do is, we have done it earlier also, that you have to consider multiplication by f on the polynomial ring, and then you get a exact sequence, and then you read. So, that is, this we have done, but not in this format, but the idea is clear that you have to consider a multiplication map by f on the polynomial ring, then write the short exact sequence, and from there you write the dimensions. Okay. Okay. Now, again the note that if you have two ideals A and B in the polynomial ring, and let us say homogeneous ideals, then I want to check that the Hilbert series for the sum ideal plus Hilbert series for the intersection is same as Hilbert series for the ideal A plus Hilbert series for the ideal B. So, you should write T here actually. This is like this, we prove this kind of formula in almost every subject. Now, linear algebra you prove this, even set theory you prove this, that is inclusion, exclusion, etc. So, this is, you can say, inclusion exclusion for the Hilbert series. This is not so difficult to prove. Again, I will just indicate the step. You see, you consider the map from A less equal to m to A plus B less equal to m mod B less equal to m. This is clear, the notation. This means the polynomials here of degree up to m and so on, right. And there is a natural map here which is surjective. Just going bar, right. So, f going to f bar, that is the map. What is the kernel? Kernel of this map is precisely A intersection B less equal to m. Once we have that, then you will get an exact sequence, and then you go mod these guys. So, that means you work in this big vector space k x1 to xn less equal to m, this vector space, these are all their subspaces, right. You work in this vector space, and then when you go mod this, then you get a formula, you know, from the short exact sequence, no, plus minus that formula precisely will give you this one.